For responding to unprecedented challenges facing power grids, we created GridMind, an artificial intelligence system for predictive control. Based on a digital twin and deep learning, it anticipates and prevents problems by transitioning from reactive management to predictive control.
Good afternoon. We present a demonstration of the Distributed Energy Network Simulator. This simulator consists of 132 energy nodes connected to each other by electrical cables, single-phase, two-phase, and three-phase. Red triangles represent nodes under load, that is, nodes containing buildings, structures, and so on connected to them. There are also a number of regulators represented by yellow squares, which are transformers with variable transformation ratios. The system also includes solar panels that operate in the mode of supplying the general network in case of voltage sags. Dark blue dots represent transit energy nodes without load, and voltage sources are represented by asterisks. On the left is the control panel of this simulator, a reset button, a network analysis button for all nodes, a cascade control button, or manual control, and an artificial intelligence control button using a trained neural network. Also, in the settings we set an additional load on the entire network above the norm, plus 20% of the nominal value, and below there are 3 sliders with which you can set goals and operating conditions. Introduction to the network. The network is a simulator of a real energy network. Each node is connected by cables with resistive parameters, characteristics, cross-section, active resistance losses, certain length, and so on. Each node has its own load, described in separate files, and the network data can be transformed to meet the needs of any customer. Let's start by setting the initial parameters. Set the outdoor temperature, let it be 34 degrees, the month, let it be July, and set an additional load on a specific node called the test node. We have allocated an additional network node on which we will conduct further experiments. If we now press the network analysis button, the simulator will perform calculations and determine the state of each node. You see that after setting the additional load, and also in the settings we set plus 20%, a number of nodes have turned blue, which indicates that these nodes are in voltage sag mode. They do not receive enough voltage to operate their load equipment. Here you can also see the node numbers and corresponding readings for each of the presented nodes. First, let's launch cascade control for a specific node. Let's take the test node as the basis. First, let's look at its characteristics. Click with the left mouse button. Here are the voltage graphs, current graphs, and power consumption graphs on this node for each phase. Also, the console displays data on the operation of this node over 24 hours. Let's apply manual cascade control to this node. Press the cascade control button. The system will now try to equalize the voltage at this node and bring it to normal. Here you see graphs of the same voltage, current, and power at this node, as well as a horizontal line and vertical marks indicating when additional switching of voltage regulators was activated. We see that a number of nodes have returned to normal. However, a number of nodes have turned from blue to orange. This indicates that some nodes have switched to overvoltage mode. This is visible in this information. Our test node, which had insufficient voltage, has switched to overvoltage. This does not quite satisfy us, so the problem is not solved. Therefore, we apply our artificial intelligence to this system, a trained neural network that will try to bring all nodes to normal. The system is processing. Here you see the change in voltage, current, and power at this node, as well as the operation of all switches on the voltage regulators. From the picture you can see that all nodes have returned to normal operating conditions. We can run network analysis again and make sure that all nodes are in working condition and the voltage is within normal limits. Here, just above, you can see the position of each of the 7 voltage regulators and the position of their switches. The neural network has worked in such a way as to solve not only the local problem on the test node, but also the problem of overvoltage or insufficient voltage on each of the nodes presented in this system. This simulator also has the ability to enable abnormal situations, in particular short-circuit modes or line breaks on any of the nodes. Let's give an example of a short circuit. Select Short Circuit, select any of the nodes, select this left node with a mouse click. The graph shows that all three phases have gone into short circuit mode. Here they are presented, voltage is practically zero, parasitic voltage is shown here. Accordingly, it is visually clear that the entire energy network is in failure mode on all nodes, since they do not receive proper voltage, and the problem area is marked here. If we now run network analysis, data will be presented for each node. Here it is clearly visible that on many nodes the voltage is below normal, which is understandable, because a short circuit occurred on one of the lines, which actually affects the entire network. Let's perform a reset. Of course, artificial intelligence cannot solve the problem of a short circuit in the network or a line break, but it can solve the problem of redistributing energy between other nodes that can be kept in operation until the line problem is resolved. Thank you for your attention.